All right. So here's a problem. Remember, we're trying to write equations for shear force and bending moment. This is a problem. If you look up here, you'll notice it's different from the ones we worked earlier, in that the loading function, in this case there's a uniform load, is not continuous across the beam. Right? So I have a loading function that's continuous over the first 12 feet, and then I have a different one that's valid over the last 8. So I'm going to have to break this up into 2 pieces and write 2 sets of equations. We haven't done that before. But it sounds exciting, doesn't it?
Yes.
So let's start with that. So I'll just kind of show you what I want to do is first I'm going to write an equation that's valid during this first 12 feet. So I can make a cut anywhere I want in that 12 feet. And I can decide, do I want to work the left-hand free body or the right-hand free body? It's completely up to you. If you want to work the left hand, you're going to have to find some reactions. You're going to have to find a shear force and a bending moment reaction.
The right side.
If you work the right-hand side, you don't, but you're going to get some strange notation because remember, we usually measure our x from the left. So you're going to get some interesting stuff here. Can do it. The second one, I'll use a different color for that. So for the second set of equations, which will be valid between 12 and 20, if I make a cut anywhere there, and I look to the left, I can draw a free body of the whole left side or a free body of just the right-hand side. I think you can see the right-hand side is going to be way easier to deal with, regardless of the... And in that case, too, my x would be from the left. So I think what I'm going to do today is just always use the right-hand side free body, just to show you how it works. So let's start with the first set of equations, which are valid from 0 to 12. So what I like to do is just actually put a little note to myself. Hey, this equation is only good between 0 and 12. Okay? And I'm going to look at the right-hand free body. So let's see if I can draw that. So that means I'll have from the left side, this will be x. And then I'll have a partial loading. And then I'll have this load out here on the end. So I'm just transferring my information. Now, what's this distance here? Well, I know the total distance is 12. So at any distance x, this little piece here is going to be what? 12 minus x. Right? And what's this little distance out here? It's 8. You have to take some time to make sure that you get all your dimensioning right, and the parts that are functions of x are functions of x. Now on this cut face, I'm going to assume positive shear force and positive bending moment. Those are the 2 things I'm trying to find.
If you know that in the problem you don't have any internal reactions in the horizontal direction, we just not worry about drawing it.
Yep.
Okay.
Yeah, and also I'm only asking for shear and bending. If I ask for an axial equation, then you'd have to include it. But usually in a beam, there's not much horizontal loading. Now I got to deal with this thing. This is still going to be a funny thing. So I'm going to get a concentrated equivalent, and just to help myself, I'm going to say that's some force D, some force F, and the distance will be D. So what is that force F? Well, it's a rectangle, so it's going to be the base. The base is 12 minus x, and then the height is 4 kips per foot. So my function is going to be 48 minus 4x. Not my function, my force. And then what's the distance? Well, it's always whatever the base is divided by 2, right? So I'll just leave it this way. I'll just leave it as x minus 12 divided by 2. In fact, you know what? I think I'll go back and leave that, take that out, and just leave it like this, x minus 12 times 4. And you'll see why in a second. I think that's all we need. So this is the only interesting thing, is you end up with these kind of adjustable links when you cut it. So now what we're going to do is we're going to sum forces. We're going to sum moments about the cut to find my moment. So I'm going to make sure that this right-hand free body is in equilibrium. So I use right-hand rule, so what's my moment here? Is it positive or negative? Negative. About the cut face, does this force F create positive or negative moment?
Negative moment.
Negative. Everybody see that? I'm using right-hand rule. So that'll be negative the force. What's the force? It's 4 times 12 minus x. And then times distance, which is 12 minus x over 2. And what else?
20.
I got this guy. Is that going to create positive or negative moment?
Negative.
Negative. So the force is 20. What's the distance from the cut to the end?
12 minus x plus 8.
Yeah, 12 minus x plus 8 is 20 minus x. So solve for the moment. The moment is simply going to be, move it to the other side of the equation. I'm just going to leave all that stuff alone. So I'm not even going to try to expand it. Don't waste your time. So I've got a 4 here and a 2 there, so that's going to give me a 2 on top, and then I have 12 minus x squared. Then I got this stuff down here at the end. If you want to multiply that out, you can, or you can just leave it. And that is an equation for the moment. And that will have units of kip and feet. Now, how can I check that? Do I know the moment anywhere between 0 and 12? Right now, the answer is no. If I had the reaction moment, then I could check this equation at x equals 0 and it would match. So I don't have that. So that's one disadvantage of not going ahead and getting your reaction moments. You don't have anything to check with right now. What do you think the moment should be at A? Positive or negative? Bending moment. Which way is the beam going to bend?
Negative.
It's going to kind of bend like this, right? That's kind of half a frown, so it should be negative bending moment. If I put in x equals 0 here, do I get a negative answer? I do. This is negative, and this is negative. I get a negative. So at least qualitatively, I have the right sign. I don't know if the value is correct, but I know it's at least predicting the right direction. So I'll just have to leave that one alone. Then I can sum forces in the y direction to get the shear. Excuse me. So look at the shear. Look at all the forces. I'm going to assume up is positive. What's the shear? It's positive. My F force is negative, so it'll be minus. And what is my F force? It's 4 times 12 minus x. And then I have 20 also acting down. Excuse me. So it's pretty easy to solve for the shear. So my shear is going to be equal to what? It looks like something's not right. What did I do wrong? No, maybe it is right. Everything goes to the other side, right? So it'll be 4, 12 minus x plus 20. And that should all have units of kips. If you take the derivative of the moment, do you get the shear? I think if you look at the last term, you can see it is. What's the derivative of this with respect to x? 20. What's the derivative of this with respect to x? It's that. So it does work. So at least you got that. So I will write here that if you do take the derivative of the moment with respect to x, do you get the shear? And the answer is yeah. So that should make you feel pretty good about that. Okay? So now we'll do the next part. I think I can squeeze it in down here. So now I'm looking at an equation that's going to be valid between 12 and 20. And this one will be a lot easier to pull off. It's just going to be the right-hand side. So there's my free body diagram with the 20 kip force on the right. So from the left to the cut is x. So what's the remaining segment of the beam? It'd be the total length minus x. The total length is 20. So this little piece here is 20 minus x. And at the cut surface, again, I'll have positive shear and positive bending moment. So just like we did before, we can sum moments at the cut. Make sure it's in equilibrium. And what do we have? What kind of moment is this with right-hand rule? Negative. So I have negative the moment. This 20 kip force about the cut creates positive or negative moment? Negative. And it's going to be force of 20 and distance of 20 minus x. So it looks like my moment is going to be equal to minus 20 minus x. And that will be kip feet. Now one thing I can do right quick is where these two sets of equations share a value, so this one goes 0 to 12, this one's 12 to 20, so at 12 they should predict the same value. If you put in 12 here, what do you get? Well, this term goes to 0, and you're left with that term, which looks just like that term. You don't even have to compute it. They will predict the same value of moment, so that should be comforting. What about the shear value? Well, let's just go ahead and sum the forces in the y direction. Make sure we have equilibrium. Well, our shear is acting up, so that's positive. We have 20 acting down. That's a pretty easy one to solve. The shear is just equal to 20 kips. It's constant. What's the derivative of this function with respect to x? 20. So again, we have at least one quick check we can do. We know that the derivative of the moment with respect to x should be the shear, and it is. Pretty cool, huh? Done. So if I want to know the internal shear force and bending moment at x equals 6, I've got to use this set of equations. If I want to know it out here at 18, I have to use this set of equations. So be careful. They do have limits. Even though these are continuous functions, and you can plug in any value of x you wanted, and it's going to predict some value, it only has physical meaning between 0 and 12 for the first set, and 12 and 20 for the second set.
On the test, would you ask us a question like that, defined as a function of x?
Mm-hmm. For sure. Guaranteed. Well, let's see how. Yes. That's the shortest word I could think of to respond to your answer. Yes. Any other questions? All right.